Across a new paper called AgentFlow recently. So I was just going through how multi-agentic systems are evolving in the industry, and kind of like I was also facing a lot of problems in my current work. I was building, we're building kind of like complex multi-agentic systems. One crucial problem I was facing is these agents are very chaotic and do not understand what are their particular tasks, and it does not know whom to delegate and how to plan and how to coordinate between each other to figure out given a user query from the user and given back the output to the user. So I wanted to understand how does optimization happen in such a complex system rather than like simple one large language model. So in large language model, there have been a lot of research about like how to fine tune, how to increase the performance by using fine tuning, reinforcement learning, supervised fine tuning as such and all. And it's doing really good in like tasks like mathematical reasoning, coding tasks, and also like question answering, etc. But what happens if these large language models are eight small agents and talk to each other, need to figure out for a complex problem, needs to figure out how to come up with an answer. So for example, Replit, let's take an example of Replit. So it's kind of like a conversational chatbot where you can build web apps from development to like deployment by just conversing with the application. So it's on the back end, it's a multi-agentic system. It may have like multiple agents, like one is a coding agent where the agent's responsibility is to just like write codes, and there may be a unit test casing agent, like where kind of like its job is to just write unit test cases and figure out if any unit test cases does not pass. One other agent would be just to write execute this code and figure out if there's any errors coming up. Another agent would be a deployment agent where it deploys to the cloud. So all of these agents need to understand what are the individual tasks and also figure out what is the correct plan, how to work with each other given a user query like build a web app for an e-commerce website, figure out who has to do what, and finally end up with a e-commerce website deployed on cloud. So for that, uh, we have seen that a large language model with billions of parameters, it is very difficult for them to kind of do these complex tasks. They may answer given a question like, can you give me an end-to-end HTML website where you can like where it is an e-commerce website, it can give you all the code. But for doing all of these tasks like a human, it needs to have multiple agents talking to each other. Maybe these different agents can be different big large language models with billions of parameters working with across each other. But the main pain point comes with these billions of parameters models. You cannot fine tune easily apart from using a large scale GPU to fine tune these models. What happens if we use small language models and kind of like break these complex problems to smaller chunks of problems, and these smaller models address those smaller problems basically. These smaller language models can then collaborate with each other. Maybe if you're using like like just a single large language model with billions of parameters, you can actually use 5 to 10 small language models and break the big problem into smaller chunks and figure out a way to do it. So that's where it becomes really interesting. So this particular paper talks about agent flow. So what it talks about is it's kind of like a multi-agent system optimization for effective planning and tool use. So it figures out how to optimize planning of these steps to figure out given a query or complex query, figure out the steps what it needs to do, plan it out, how to coordinate with these different smaller agents, and then appropriately use the tools given to these agents to come up with a final answer. So it talks about very interesting point is it actually outperforms a 7 billion model outperforms a 200 billion model, which is a GPT-4o. So that's a very interesting thing. So what is happening here is basically we are talking about a 200 billion model, which is really smart and all of that. It's more to the crux where a small 7 billion model understands how to interact with different smaller 7 billion models and perform a complex address a complex problem is more important than like fine tuning a big billions of parameters of model. So you just like instead of using a billion parameter model, you can just use smaller models and it fine tune it to understand how to plan, how it figures out the coordination. That is more significant than just fine tuning a bigger model. So given a very simple crude example, I would think about it as in a car you don't need to really figure out putting the best possible engine, putting the best possible tires, and putting the best possible for example steering and like other brake system, etc. So but in the end it talks about even if you put an average quality of these particular parts of the vehicle, like an average tire, an average engine, and an average brake system, the fine tuning, the coordination between all of these systems is a lot more significant, gives a lot more significant uh, uh, like performance lift than fine tuning each and every part differently. So that's the crux of the whole paper. So if you see here, what's broke in the current agentic system is basically we are training monolithical tools using LLMs. So we are training like GPT-4 or GPT-5 or Llama 80 billion, which are really big models, and we are giving certain tools to it, but we're trying we are trying to tune that model to utilize these tools efficiently, which becomes very difficult for us to tune with like I number of GPUs. The second one is long horizon reasoning. So these kind of 80 billion parameter or like 200 billion parameter models works very well for like maybe like 5 steps max. Like it's kind if I tell step 1 do this, step 2 do this, step 3 do this, and step 5 do this, and you get the final answer, it can somehow figure out how to reason. Like, okay, if I do step 1, if I miss step 1, then I can go use a different kind of a step to end up with step 5. So it can take different routes until maybe like 5 steps max. But what happens if the number of steps is like 15 to 20? So it becomes a long horizon to completely to reach the final answer. You need to take 15 to 20 steps to reach the final answer. And for these models to understand how to reach that 15 to 20 steps to figure out the answer, the reasoning part helps us to figure out it can take multiple paths to reach that final answer. So for doing that, we need to like train these large language models to reason to reach the final answer. So I'll talk about more in the as I come through. And third one is sparse rewards. So for reaching this final answer after 15 to 20 steps, you only get to know that after that 15 to 20 steps, you did the answer right or you did the answer wrong. But how do we give those rewards to each and every step of across the path? If each and every step gets the right number of reward and good, like with the right, given that step 1 it did really good, then we need to give good amount of rewards for it. And step 2 it did partially right, okay, they give partial rewards. So you need to have good amount of rewards for every step across the path, across the trajectory. So the sparse rewards is one which happens. So if we just tune the model just because of the final answer, then all of these steps, this is very sparse rewards. So this paper talks about how to give rewards to each and every step of the trajectory to really make the agentic system understand that okay, I can take multiple paths, but I will take the most optimal path to reach the final answer. So this is how you are like training every part of the step rather than training to the last final answer. Then performs poorly with diverse tools. Given a large language model, you can give access to web search, you can give access to Stack Overflow and all of and etc. But given like 10 to 15 tools, it needs to understand what is the capability of each tool and figure out how to efficiently utilize all of these tools to figure out the final answer. Which again, given a very big model, even majority of the times you kind of like do prompt heuristics where you write the prompt telling that each and every functionality of the tool, and then it figures out okay, I can do this. But what if you kind of like train the model to understand like with a set of examples that most of the time to reach this final answer you have used tool A, tool B and tool C, and to for a different question I've used tool A, tool D and tool C. So you have different trajectories of tool usage as well. So for a very new kind of a question, it can figure out that tool A is always used for this particular thing, tool B is always used for this particular task, and tool C is always. So it figures out the kind of reasoning of tool usage as well. So the last one is inefficient in new scenarios. So basically, given a new scenario, when you play just with prompt, what happens is you kind of like it does not understand how to think about by itself, how to figure out for a new scenario. But here, since it's developed reasoning capabilities, it knows that to reach the final answer, I've seen that okay, if I break this down problem by step like 1 to 15, step 1 I can take Google search, step 2 I can do Stack Overflow. Like that, it figures out the reasoning of the tools using the reasoning of the tools, and then figures out how to reach the answer. So that's the really brilliance of this particular part. So we are talking about how do we train multi-agentic systems to coordinate with each other efficiently, and by optimizing it with understanding and rewarding the system for every step of the trajectory to reach the final answer, rather than just tuning these agentic systems on the final answer to telling that okay, this answer is right or wrong, and you need to like either use a monolithical LLM model to figure out like tune that model to figure out the answer. So for that, okay, before going there, so what I can show you is of course like this particular part, what it talks about is you can see that uh, it is doing really good, like this AgentFlow model. It's a 7 billion model basically here, and it's outperforming one of like the biggest models in different benchmarking datasets. So these are different datasets called 2Wiki or PodQA, GAI, and all of that. These are different. What do you say? Again, these are agentic systems. This is for search capabilities. This is for search again. This is for math. So they're trying to figure out if this model outperforms in different capabilities to comparing to different like Qwen 2.5, 7 billion, GPT-4o, research is another one, AutoGen, 2RL and TIR. So if you see, these are all 7 billion models, and there is also a 200 million model, it's GPT-4o. So if you see, it has the red is the AgentFlow, and which has outperformed all of these different models comparatively. And if you see here, the blue is what is the red is the AgentFlow, basically the model which is like outperforming like performing really good in all of these different benchmarking datasets. I'll talk about more of like what's called GRPO. They're using GRPO as reinforcement learning to tune this, optimize the planning and tool usage. Apart from that, when we spoke about this monolithical tool using LLMs, right? So So how people are using right now an LLM is basically given like a LLM like GPT-4o, and given it access like tools, either a tool like different tools, Google search tools, Stack Overflow tool, and LLM will first think like kind of like okay, given a query, I need to like okay, given a query like create a function of using Fibonacci series, for example, to run multiple times recursively, and give me a final answer basically. So it starts thinking, okay, the user is asking to first figure out if Fibonacci series code, and then the user is talking about optimizing it with different algorithms. So these are like step-by-step thinking part of it, and then it does the right tool calls. Okay, first let me search Google search for it, and the second thing, let me search for Stack Overflow. Basically, does the right tool calls and figures out the answer, and then gives the final answer to it. So these are just one model figuring out an end-to-end answer, like given a problem, by thinking and calling the right tools and giving the final answer. But coming here, these are called tool integrated reasoning models. So we are giving access of tools to a large language model, and it is the large language model is also reasoning and then finding out how to use these tools to figure out an answer, the final answer. And this is the same kind of like the architecture, just that the LLMs can not only use the what do you say, the its own tools, but also the output of other tools. It can take the output of the other tools as an answer to it, and then use this to figure out an answer finally. But what happens if these are training free agentic systems? So what we are doing here is each module is a large language model. Here, this is one monolithical model, but here each module is one large language model. So module one finishes, one large language model gives you an answer. Then this answer goes to module two. It does its own work and gives you an answer. Maybe like think about the same example of uh, like okay, do the same example of the Fibonacci series. Module one is Google search. Module two is Stack Overflow search. Module three is maybe synthesizing all the right information. Module four is coding. So it every module is one large language model, and figures out an answer finally and gives an answer out. And these are other types of architecture. These are sequential, but these are more of like working together asynchronously or independently. Module one and module two figures out, given a query, okay, I'll do Google search, you go to Stack Overflow search, and the final answer. Module three's work is to take the answers out from these two modules and synthesize the information, and the last module will just code the final answer, give the answer out as basically. So these are the different architectures or ways like how the multi-agentic systems are working right now. Again, the problem is, if you see, all of these are large language models, and each of these modules are being fine-tuned. For module one to figure out the Google search, you're fine-tuning this module one to do a really efficient Google search. You'll tell that okay, you've given certain examples. You kind of like tell that okay, Google search only if you use these important keywords, the Google search performance is increasing really good. Can you make, and this kind of efficiency optimization you do using prompts. So module one is an LLM, right? You kind of write a prompt, make it a lot more efficient in the prompt, telling that write these kind of keywords, and so that your Google search is optimized, and search in these kind of websites, which is a lot more verified information and all that. So you kind of like tune these different models independently to reach the final answer. But you're not optimizing with these coordinations. How the answer going to the next module, these answer going to the next module, but not here, but majorly in this architecture, where how module one and module two talks to each other, and module one and module three talks to module one and module two to get the right answers, and how this passes to the next module. And if there is any thing which is wrong, it kind of like needs to have a feedback loop and kind of like figure it out by itself. So this is where the optimization takes place. But currently all these models are being like optimized on single monolithical large language models. Now, what AgentFlow is basically telling us, it's a trainable. That's really important, because one of the things are these are like this optimization of coordination is not trainable in most of the systems what we spoke about there. So these are trainable in the Flow agentic framework that coordinate between four modules. So this AgentFlow framework is going to give you four modules. One is called the planner, second is executor, third is verifier, and fourth one is generator. All of these can or cannot be the same large language model. Maybe for example, you can use just like let's take an example of Quen 7 billion model. You can use Quen 7 billion model as a planner, Quen 7 billion model as an executor, verifier also the same, and generator also the same. But we also can also use Quen 7 billion as a planner, maybe like another small language model like GPT or as a executor, and verifier as another Microsoft small language model. So generator as a different model. You can also use different models, but you're giving specific tasks to these small models. So you're making these models with specific identities. Your main task is to plan, your main task is to execute, your main task is to verify, and your main task is to collect all the information and give the right answer. So we have specific responsibilities for these agents. Now, all of these agents are as a evolving memory, and it is accessible by each of these modules. So it talks about okay, I finished my planning and I update my memory. I finished my executing based on the plan which the planner did, and I will update my memory. So that's the evolving memory part which is talking about. and directly optimize the spanner inside the multi-turn loop. So what is talking here is, so the optimization happens only for the planner, not the executor, refiner, and generator. So we are making the planner become a lot more smarter. So it so that by planning way more efficiently. So we are increasing the brain part of it than not the other like ands legs part of it. So the ands legs are going to execute, and verifier would be your highs, maybe generator would be your like the final output or whatever you're doing, basically. So the planner is your brain. So you are increasing the brain, and we are optimizing the brain basically. So to train and on policy in live environments, so we spoke about fine-tuning large language models and reinforcement learning. So by training on policy in live environments, what we are talking about is we are going to put this in live environments, and we are going to train the policy in the live environment using group relative policy optimization, GRPO. So this is being used for many of the large language models right now as well, like DeepSeek R1, which is using, and they show that you need very less number of training samples to really optimize the model's behavior. So that's the reason I think this is like really performing really good of how do we optimize the collaboration or the planning part of it as well. So, and these are the things which tackles long horizon. Sparse reward credit. I'll talked about that once I show the architecture. So as I said, right, given a query, so okay, let me just tell. Can you write a function? Can you write a function for Fibonacci series again? So the query is this, and the toolkit set is a Google search and a Python coder and a Wikipedia search and a Stack Overflow search. These are the toolkit set which is available. The planner plans the query. Okay, if okay, the query is about writing a function for Fibonacci series. Let me first search Google. So the action one would be search to Google. Executor's job is given this toolkit set and given this action by the planner, I just have to search to Google. And the verifier sees the planner's plan, the action basically, and the executor's results, and verifies if it's the right thing or the wrong thing. So it just verifies and gives a thumbs up and a thumbs down. Based on this thumbs up and thumbs down, this updates the memory, telling that okay, this was the action, this was the result, and this was the verifier telling that it's a thumbs up or a thumbs down. The next, this memory is used by the planner again to understand, okay, Google search did right, it found all the right articles or the right information. Now I need to search Stack Overflow maybe, like okay, that will give me more coding examples. So the action 2 would be the search Stack Overflow. Executor will just do Stack Overflow based on the available toolkit set, calling the right tools again, and verifier gives a thumbs up and thumbs down. Again, this output goes back to the memory here, updating, telling that okay, this was the action, this was the executor result, and this was the thumbs up or thumbs down. And if you see, these are different turns. That's what step 1 to step 5. Step 1 to Google search, step 2 do Stack Overflow search, step 3 collate the results, step 4 write the function. So these are different steps in the model, and as you go through the steps, the memory becomes a lot more, the context becomes a lot more richer. So that's what is happening here. And in the end, the final executor verifier gives it like the final okay, code is here. The generator collates the code and gives it back the answer as an output. So this is the final output. So as I said, right, see these are different turns. What happens in the traditional systems is these different turns goes through, and you kind of like train one single model with the final answer and tell okay, this answer was right and this answer was wrong at the final answer, and then train this the whole single monolithical model. But here, if you see here, there's a planner, executor, and verifier. They have distinct responsibilities, and also at every turn you can now tell okay, this did right, this did wrong, and this did right to this did wrong to reach the final answer. Now every step you know what was right and what was wrong, so you kind of like now you can tune the steps to reach the right trajectory basically. So that's the main crux of this paper. So now on the right side, what they're talking about is, as we spoke about before, right, we are only going to train the planner module and not the executor verifier module basically. Why? We are basically enhancing the brain, not the executor and the verifier. So the planner takes the query, K is the tool set, the toolkit set, what are the tools available, and empty is the current state of the memory. When you start, it will be empty. And the planner takes, okay, call Google search, it's just action T. Okay, so from this action T, this goes back to the executor, as I said here, action T and the available toolkit set. Executor's job is to call the right tool. Okay, action T is do Google search, K is the toolkit set, the executor's job is just to figure out the result for it. So ET is the executor's results. This ET goes to verifier. Verifier gets query, the executor's results, and the current state of the memory, which is usually blank when you start. Verifier just gives thumbs up or thumbs down if you see this wrong or right. And this VT goes and updates the memory to empty plus one, which is an updated memory, telling that okay, this was the query, this was the executor result, this was the last state of memory, and this was the verifier's result, the right or wrong, and empty plus one is updated. So as I said, only the planner module is like updated, and the rest of the other two modules are static. Now that's why if you say it tackles long horizon. So since now we are going to like give rewards to each and every step, telling this is right, this is wrong, this is right. So you kind of like you can tackle long horizon problems, telling that okay, if I can take like different paths like this to reach the final destination. and sparse reward credit assignment by converting multi-turn optimization. I'll talk about more of that. So a trajectory is basically given by tau. Tau is basically a set of like S1, which is state plus memory, A1, which is planner's action through plus tool call, E1 is executor result, and like different, like S1 would be the first turns and S2 will be like different like turns basically and different things. This is a trajectory, as I said, right? Your turn one would call this is 10 1 state, and then it can go to like this and then go like this trajectory, and but for reaching this result you can also take a different path like this and go back to this result. So it can have for every part or a turn you can have a state action, so a state plus memory action and an executor, and all the turns part of it will become a trajectory. Now talking about this formula, how the agent flow workflow is like with four distinct modules, and how it takes uses these four different modules turn by turn to figure out the final answer in multiple turns. But before going to how to optimize these different turns and how to optimize the entire system, let's talk about like the few formulas which is like backing this whole optimization part. And as I just spoke to you about like what is tau. Tau is like the trajectory, and it is a collection of different state memory planner action and execution result, and every one year in the subscript is the turn number 1 to t. Okay, now before that let's cover what is reinforcement learning. So if you want to use reinforcement learning for a simple large language model like llama 80 billion open source model, so you kind of like for every given query you get an output, and if you know this output is right you get a particular reward. So you kind of like train this 80 billion parameter model. If you, for given a query, if the output is right you give a reward to that particular model. And also this becomes like step by step. Okay, the first step, okay, we call it as rollouts. In the first rollout we know that okay, the query for the given query the output was correct, and what is the current policy. So the current policy, the pi theta is the current policy, and pi reference is the base policy. Base policy is the base model, which is like the llama 80 billion without any fine tuning or without any reinforcement learning. So we are kind of like optimizing the expectation of getting the highest rewards for a given query and giving it for a given output, but also penalizing for the policies to become too away from the base model. So as you roll out by 1, 2, 3, 4, 5, you kind of like can also become too farther away from the base model. So you're kind of like penalizing to go farther away from the base model, but also kind of like giving a good score because you're getting high rewards. So you're basically learning good things. So the model is learning the right way, but also I want the model to learn the right way by not diverging from the base policy. So that's why if you see reward, KO is the outcome based reward. Pi reference is a reference model to prevent policy collapse. By policy collapses, we don't want the model to become too different from the base model. We want it to stay near to the base model, but also learn the right parameters by staying near to the model base policy. And beta is a hyperparameter, which is like you do it, you kind of like figure it out during the training part. So it controls the KL regularization. That is like how much penalization you can give for this like the how farther away is the base model, the current policy to the base policy. So why I'm talking about this is the fundamental of reinforcement learning. We need to maximize the expectations of the rewards. Okay, so for doing that, so let me another formula again. I just want to touch upon what is this particular framework, what is it talking about. So we need, this is the major, if you want to put the whole framework into a formula, this is what the formula says. So there's like a p theta, and there is action, executor result, and verify result, and 1 to t is the one multi-turn, like turn 1 to turn n, given a query. So what is called like, it's kind of like probability of the policy of choosing these actions, executions, and these verifications in these multiple turns for a given output given a query. So you kind of like this, what we're telling is these are explicit realizations of the latent reasoning chain. So it's kind of like your reasoning chain. For a given query, I can take these different kind of like trajectories, but I also know that like there's a latent reasoning of how if I take this trajectory I'll get this output, if I take this trajectory I'll go to this output. So there are different ways, and this is the latent reasoning part which the model learns, and this is what we need to learn. We need to learn, given a query, the model to reach the particular output, we need to learn the different actions, executors, and verifiers for different turns, then the probability of it. And what it talks about is it's just a multiplication of from the turn 1 to turn t. It's just a multiplication of the action, the planner's output, the executors of like function, and the verification function. And if you see planner policy is basically what is the action t given q, the toolset k, and the memory t. Execution function is basically what is the execution result given action t, what is the result given the action t and the toolset k. Verifier is given the query, given the execution result, given the memory t, what is the verifier result. It's just a multiplication of these three functions. So like if you take all of this, is where you optimize the probability of getting that latent reasoning chain basically. So this is the entire agentic, like this framework called AgentFlow, putting in one formula. Now talking about, we spoke about what is reinforcement learning, maximizing the expectations of the rewards by also not while changing the policy by not diverging the policy as much as we want, like as much as the base model basically. So now the policy optimization objective is, this is the loss function. We are telling the expectation is basically the trajectory is for the current policy is basically the reward for the trajectory. So we need to figure out like the loss function is the expectation of the reward of the trajectory, and we need to maximize the loss function. So we need to maximize the reward for the particular trajectory is what they want to do. This is the policy optimization objective. And a rollout tau is the sequence of decisions, and this rollout tau is the trajectory which we spoke about earlier, right? It is the collection of state, execute result, verify result for multi-turns and for step 1 to step t. That's what is the sequence of decisions at 1 to t generated on policy. The final output reward broadcasting. How is this final? We know that we need to find the maximum of the rewards, and how is the rewards calculated basically. What we are telling is, we spoke about in the monolithical policy that given one large language model, we can tell, okay, create a function for Fibonacci series. A large language model like 200 billion model will generate a final result with an answer, and you can either a human or a LLM as a judge can tell this is the right answer or wrong answer, and then we can tune the single monolithical large language model with this right or wrong, maybe 80% right, 100% right, and kind of like tune the model. But what happens when there are multi-turns? Like there are like small turns as we saw in this particular multi-agentic system, and how to give rewards to each and every turn, basically telling step 1 it did right, step 2 it did wrong, but it did partially right. So to give like turn by turn broadcasting of rewards. So what is it telling is, our OQY is between is either 0 or 1 is assigned by an LLM as a judge. The final answer is like using LLM as a judge gives either 0 or 1, telling wrong or right. This propagates a trajectory level success signaling back through the reasoning chain. So we are going to give this particular reward to all. For example, if the final answer is right, we are going to give step 1 1, step 2 2, step 3 3, all of this particular step 1 to step 10 or step t a reward of 1. If the final answer is wrong, we're going to give all the steps as 0. As we go through multiple samples of it, we're going to figure out a way where like, okay, given this particular question and given this particular answer, we get like, we know the correct trajectory to take basically, which will reach the final answer. So I'll talk to more about that. For example, I can show you here what happens. So the flow GRPO basically is, so this is just the reinforcement learning, like the normal policy optimization. But the best part of it comes when it's called GRPO, group relative policy optimization. What does this mean is, a policy. So given a query, what we spoke, given a memory, which is like very blank in the beginning, and given the tool set, going to the policy model or the planner basically. So this planner generates multiple outputs. So it can generate G responses. Like, okay, for example, give a function for Fibonacci series. It can generate 5 different answers. Let it generate 5 different answers. It's fine. So like answer 1, answer 2. It may be that answer 1 is right, answer 2 is wrong, answer 3 is right, answer G is correct. So let it generate multiple responses. So these responses may have taken different trajectories again. So response 1 may take one A1, A2, A3. Response 2 can only take only two steps, A1 and A2, and it gives the answer. Response 3 takes 5 different actions, like that, like different. So every response may have different turns to reach the final answer. Now, based on this, O1 may be right, O2 may be wrong. So the output 1 generated will be right, output 2 is wrong, output 3 is correct, and output G may be wrong. So based on this correct or wrong, we give rewards to every step of this particular response. So since this output 1 was right, we give reward 1, reward 2, reward 3 as 1. Since output 2 was wrong, we get reward 2 1, reward 2 2 as 0 0. And since reward 3 was right, we give all of these rewards like as 1. So using these the same policy model to generate multiple outputs with multiple trajectories, we figure out, okay, if I take action 1, action 2, and action 3 here, I'll release the correct output in a lot more better way. So that's the latent reasoning part, which the model will understand. So multi-turn group computation happens and updates the policy model. And as you see, the trained models are basically this is the training model, and the KL optimization happens, telling that, okay, once I use this rewards and give it back to the policy model to update the parameters, I also don't want this model to go away from the base reference model. So if I use llama 80 billion, as a first, so the weights are like frozen, and when I want to update the weights of this new model based on the rewards, I also don't want the weights to be farther away from the reference model. So that's what is the whole flow GRPO happening. So we are generating, that's why it's called group relative. That means it is generating multiple outputs and then understanding how far, like how better is each output, and figuring and optimizing the rewards based on these output between these, like the outputs generated by the same policy. So the same thing. So coming there, the formula part is flow GRPO objective is basically the loss function here is for the flow GRPO objective is 1 by G is the number of responses generated by the policy model, and 1 by T is the number of turns taken by the model. 1 by absolute of ATI is the action taken by the model. So in the end, what we are trying to do here is, this is the same, what do you say, the GRPO function, where we are kind of like, we are telling that, okay, I want to give advantage of basically what is an advantage. Again, let's talk about what is an advantage. An advantage is like the reward of the particular, so the reward of output 1 minus mean of all the rewards of all outputs divided by the standard deviation of all the rewards. So you're basically understanding how output 1 is more better than all the other outputs. So you're giving, if output 1 is the 100% the best answer, it gets a lot more higher advantage than the other outputs. And if output 2 is like, okay, 60% good, so it gets a lot more lower than output 1, but higher than output 3 and output G. So that is what is called advantage. So you're gonna giving that PI, the probability, I'll talk about what it is, and advantage for this particular thing. So this PIJT is basically for the turn T, you're telling what is the current policy's action based on the basically the memory and the previous action basically. So basically you're telling that I think ST was the state plus memory. So what you're telling is what is the action using the current model given the state and the action from 1 to j minus 1 from the previous actions. So and divided by the probability of the old policy. The whole policy is the previous turns rollouts policy. So every rollout you kind of like you figure out how different am I from the previous rollout? How different is this action from the previous rollout? And what is the advantage of that? Basically, if the advantage comes from, okay, this output was really good, and how different was this particular rollout from the previous rollout, basically. So that is what you're trying to do here, and this is a clipping part of it. You either do this or you have a clipped version of it, so that you do not sometimes you do not go out of the out of the uh, uh, like out of bounds basically. Sometimes it can become too high or too low, so you kind of like give an epsilon, which is again fixed basically. You kind of like clip it with that for this PIJT. So, and this again we spoke about the reinforcement learning part of it, right? This talks about how you're penalizing for the KL divergence of the current policy to the base reference policy, but this talks about what we spoke before about the expectations of the rewards given a query queue for an output. So this whole part of it is that part. So this is like the formula for GRPO, and this is how. So when we spoke about this is a plain vanilla GRPO, but we are using multi-turn, and this is again 1 by G is the plain vanilla GRPO. This is the extra part which has been added to the plain vanilla GRPO. It is being optimized for multi-turn policy updates, multi-turn single policy updates. So every turn you are doing a policy update rather than the plain vanilla, which is just like plain vanilla GRPO, which is there, where the total language model is being optimized by the final outcome, but not for intermediate rewards. Now, so this is the GRPO. So the main crux, as I told, right? I'll just like summarize again. These 4 different modules. We are rewarding every turn basically on the final answer and giving basically a reward for every step of the process. And we are optimizing using the flow GRPO objective function, so that then we know that okay, turn 1 was right, turn 2 was wrong, turn 3 was right, and giving rewards based on that. So this will in turn figure out this p theta of the basically the latent reasoning chain. So now what we want to see here is how is this particular model performing good across the different models, like performance analysis. So if you see here on the left hand side, we're using Quen 7 billion Winstack, Quen 14 billion, 32 billion, 7 billion, and for different benchmarking data sets. Okay. And we're using also GPT-4o, GPT-4 mini, and you see the size of it, 200 billion, 8 billion, and all that. And there are different other models as well. But if you see here, AgentFlow, how is it performing on different benchmarking data sets? And the AgentFlow is basically just a Quen 7 billion model. If you see 7 billion base refers to Quen 2.5. They're using the same model which is here as AgentFlow, using this 4 distinct modules, and also the second part of AgentFlow with Flow GRPOs, tuning this policy with Flow GRPO, tuning it to understand the latent reasoning chain. So AgentFlow is just plain vanilla Quen 2.57 billion model with those 4 distinct modules, telling planner, executor, and all of that. And the second one is you're tuning these 4 different modules, Flow GRPO. So then you compare all of these models with the final AgentFlow with Flow GRPO, and you see the delta for these different search intensive agentic, all of them are positive. Even with a 200 billion model, you get 8.2% gain from these models. So you're basically tuning the small models to understand what kind of like trajectory to take to reach the final answer, even though if it's complex. But if you just give a monolithical 2 billion GPT-4o kind of a model, it still doesn't understand how to reach the final answer in certain objectives basically. So that's one part. And again, the same way, if you see it outperforms. So all of this green color delta is compared with this 57.3 here. 57.3 minus 15.5 is 41.8. 57.3 minus 27.3 is 30. So it's compared to this AgentFlow with Flow GRPO, all of these different models. And the same way, this AgentFlow is compared with again math reasoning and scientific reasoning. And if you see, all of it outperforms even GPT-4o as well. So that's one. And the second one is how is the performance comparison of AgentFlow across different training methods. So again, different kind of like benchmarking data sets. They're using Quen 2.57 billion as frozen, and then GPT-4o as frozen. And then they thought, okay, let's just tune, so like supervised fine tune Quen 2.57 billion model and see how it performs. And if you see, it performs very poorly even with the frozen model. when it tests. So it is not able to understand how to do it. But when you use Qwen 2.57 billion with Flow GRPO, it even outperforms GPT 4o. So this talks about how important is this particular approach. It's not the model, but it's the approach which kind of like causes it to understand how to optimize planning and tool usage basically. We have not come to tool usage. I'll show you more importance of tool usage. And if you see here, tool call ratio changed by flow GRPO. This flow GRPO method, right? Kind of also, if you just use kind of like the previous after fine tuning and after fine tuning. So basically, if you just use step 0 without the base model, basically the Qwen 2 points, the 2 point, the 7 billion model, it uses these different base generator, Google search websites, these different tools in this ratios, and with an accuracy of 60%. But when you fine tune it with Flow GRPO, it reaches 77.2% with the tool usage ratio changing. So it is using this green, which is Google search a lot more number of times rather than other things like web search and Wikipedia search. It figured out that I need to use Google search, and which is giving a lot more better answers than the other ones. The same way for MetQA, it's understanding that okay, I need to decrease the MetQA. It's being using at 28.7% of base generator and 66.2 of Google search. So for MetQA, it figures out that okay, I do not have to use Google search a lot, and I'm not getting the right answers. I may have to use Wikipedia search, which is a lot more dense domain-specific data. So it kind of tunes to the way to use the right tool to increase the accuracy from 76 to 80. So this is how the tool call ratio changed by using the Flow GRPO optimization. The same way, the tool error calling rate. So if you see the across the GRPO objective like optimization, right, the error rates fall down of tool calls. So it may have been calling wrong tools in the first and step 1 for like maybe let's just take AIM 24. It used to be like 10 wrong tool calls. Now it became smaller, 6 calling error rate like by 10%, 7%, 6%, a lot more lesser basically. So the tool calling error rate is also decreased because of the optimizing through Flow GRPO. And to really see how it the advantages shown here is like through the two conversational, like the two flows of not tuning anything, the base model, to tuning with AgentFlow. So AgentFlow before Flow GRP fine tuning. That means this is just the plain vanilla Qwen 2 like 7 billion model with those 4 modules, the planner and the generator verifier and all that. And this is the AgentFlow after GRPO fine tuning. So if you see here, it kind of like initially failed with repetitive errors, but the after tuning, it kind of like it found the final answer. The first time it found the wrong answer because it called first one is Wikipedia search, Google search, Python coder, and the Python coder did not give the right answer, so it started to like loop here itself and finally fail after a certain number of turns. But here, here again, the Google search came out with the right answer. So instead of using like Wikipedia search give the wrong answer, okay, it did not find the right results. Google search gave the right answer. Python coder did give the wrong answer, but again the second turn the Python coder did give the right answer because it got optimized about how to fine tune itself, and then it gave the final answer. And it also talks about before and after fine tuning. The agent flow is basically Qwen 2.53 billion instruct. So is this GRPO objective, right? Flow GRPO, does it help with both small models? So does it only work on 7 billion models, or is it like very specific to certain size of the models, or is it like it can happen with like it can optimize or it can increase the performance for any number of size of the models? So they did the Flow GRPO optimization for 3 billion and for 7 billion, and for both of it, if you see, there are what do you say? There are performance gains. So it is invariance of the size of the model. You just use this optimization, it becomes the performance increases, and there's a lift. And this part of it talks about, so how many, if I, okay, now I've optimized it. If I just tune the number of turns to give an answer, so basically I want the answer in 3 turns, 3 steps. I want the answer in 5 steps. I want the answer in 7 steps. I want the answer in 10 steps. How is the accuracy like kind of increases? So of course, if you take 10 steps to reach an answer, it is still increasing. So that's what it's telling. Like how many number of steps you can give it to reach the final answer. Average turns and accuracy with increased T max. So if I increase the number of turns, of course, the average number of turns with you kind of like accuracy increases. So and that is the part of this particular equation here. I can increase the number of turns given, maybe I can. So usually that's an hyperparameter actually. So you can tell only I need the final answer in just 5 turns. So it's can like you kind of like fix this up. You can give the answer as maximum of 10 turns. It can be lesser than 10 turns, but maximum can be 5 or 10 turns kind of a thing. So with the increased number of turns, the accuracy seems to be increasing. So the maximum number of turns basically. So if you see the majority of it, so I think the core problem which it solves is using this Flow GRPO to optimize the planning and tool usage. It figures out how to latently reason of why is this tool used and why in a trajectory of step 1 to 15 to 20, what is the importance of each step, calling the right tool, and it figures out this latent reasoning. That's what we need to like fine tune than fine tuning the entire model as such to give the final answer. So that is what I think is super important from this paper. I think there are more things which we can work upon. This is basically is how to reward this. Even though you're giving rewards of 0 or 1 to each and every step, we can actually give rewards based on the how much of contribution each and every step does it to the final step. That's again one of the further questions we have, and we can think about how to actually bifurcate the final reward to each and every step. So tuning in that way, the multi-agentic system will understand what is the right optimal trajectory to take for a given query to reach the final answer. So that's what I think this paper talks about.